Hello, space enthusiasts and cosmic curiosity seekers. Welcome back to another episode of Overtime Q&A, where we dive deep into the wonders of the cosmos. Today, we're exploring some of the most mind-boggling concepts in the universe, the expanding universe, Starship telescopes, and the intriguing battle between quasi-stars and black holes. So, buckle up as we embark on this stellar journey through space and time. Ever wonder what mysteries unfolded in the earliest moments of the universe? What exactly is the universe expanding into? How do astronomers piece together events that happened billions of years ago? We're diving into all these cosmic questions and more in this week's episode of the Overtime Question Show. Hello, everyone. While we're still on a break from our live stream, we're excited to share another episode packed with your burning questions. These inquiries rolled in during our live streams, and even though we'd wrapped up recording, the curiosity didn't stop. From an array of space-related wonders, we think you'll find these discussions particularly thrilling. Join us for an enlightening exploration as we delve into questions from late October. For instance, Amal Goyle asked about the early stages of the universe and why we can't observe it up to its actual size. It's fascinating. Imagine if we could rewind the universe like a video. Currently, we see galaxies drifting away from us. Reversing this would visually pull them closer, giving us insights into the universe's nascent stages. Imagine a cosmic dance where galaxies hurtle towards one another, eventually gathering in a single, dense point. This isn't a scene from a sci-fi movie. It's a glimpse into the early universe, a time when everything was unimaginably hot and dense, similar to the core of a red giant star. Picture this, a universe glowing a fiery red everywhere you look, radiating at a scorching 300,000 Kelvin. Now, let's travel even further back in time, to just about 380,000 years post-Big Bang. But don't stop there. Rewind to just minutes after the universe's birth. Here, conditions were so extreme that the entire cosmos mirrored the intense heat and density of our sun's core. For a brief pivotal span of about 20 minutes, the universe was a forge where hydrogen transformed into helium through nuclear fusion. This critical period set the stage for the chemical makeup we observe today, with hydrogen making up 75% and helium 25% of the elemental universe. But even before this elemental alchemy, the universe was a place of intense forces, where the strong and weak nuclear forces merged, weaving together with electromagnetism. Curious to explore deeper? There are fantastic resources, like the first 3 minutes a book that dives into these formative moments of cosmic history. It's a thrilling journey back to the very beginnings of everything. Have you ever wondered why we can't grasp the full size of the universe or what it's expanding into? These are some of the cosmic mysteries that even the best books on astronomy try to unpack. The reason we can't see the entire universe is straightforward light. The fastest messenger in the cosmos has had only about 13.8 billion years to travel since the Big Bang. That means the farthest reaches of the universe are still beyond our visual grasp. As time marches on, more light will reach us, slowly unveiling more cosmic secrets. But here's a brain teaser we often encounter. What is the universe expanding into? This question bends our understanding of space. If the universe is infinite, then the concept of it expanding into something doesn't really apply. It's infinite. On the other hand, if the universe is finite, imagine it as a sort of cosmic donut. Travel in one direction long enough, and you'll end up right back where you started. It's a mind-bending idea that challenges our perceptions of space and time. Picture this: when we envision the universe, many of us imagine a massive sphere ballooning out into, well, something. But that's not quite how it works. There's no outside to expand into space, isn't stretching into a pre-existing void. This challenges the way we typically think about space itself, propelling us deep into the heart of cosmic mysteries. Now, let's tackle a common conundrum in astronomy that trips up even the savviest space enthusiasts. If we say looking further into space means looking back in time, Doesn't that contradict the theory of relativity, which suggests what we see is happening now? Here's where it gets interesting. Due to relativity, events occur at different times depending on where you are in the universe. Consider a star that explodes. You might think that star just burst into supernova brilliance. Meanwhile, someone else might argue, no, that explosion happened 10,000 years ago, and we're just now catching the light show. So, who's right? Well, what about the observer near a supermassive black hole, where time stretches thin? Or someone traveling at nearly the speed of light, experiencing time in a slow crawl? The question of when takes on new layers, challenging our perceptions of time and space. Imagine you're on the far side of the Milky Way, experiencing a staggering 30,000 years of time dilation. Time, as we understand it, stretches far beyond our everyday experiences. This brings us to an intriguing aspect of cosmic events. When exactly do they occur? It turns out the answer hinges on your speed and the gravitational forces at play around you. When we talk about observing celestial phenomena, such as a supernova, things get even more fascinating. You might say, the supernova exploded right now because you are witnessing it now. But in reality, that brilliant flash occurred in the past. You were simply unaware until the light reached you. This introduces the concept of the speed of causality, which dictates that events propagate through the universe at the speed of light. So, if we consider an event happening based on our local frame of reference, it isn't quite accurate to declare it occurred 10,000 years ago without context. Time in the cosmos isn't a universal constant, but a variable that depends dramatically on where you are and how fast you're moving. Saying it happened now, when you see it, rather than it happened 10,000 years ago, aligns more logically with our understanding of time and relativity. Imagine trying to explain the complexities of cosmic time dilation, where speeds and gravity wells stretch and warp time itself. It can make your head spin, and believe me, it's enough to drive anyone a bit crazy. I've learned to tread lightly on this topic because it often invites a barrage of, responses that can wear you down. Now, about the concept of look-back time that we often hear about, it's not quite accurate. A more precise term would be the speed of causality, which refers to the maximum rate at which information or influence can travel through the universe. It's a fascinating, if somewhat humorous, point of contention among those of us who cherish precision in communication. I often get asked which misconceptions frustrate me the most, and it's this one. It's all about striving for accuracy, and then suddenly, you're caught up in a debate you never wanted. But what can you do? You nod, smile, and move on. Imagine jamming an 8-meter telescope into Starship, equipped with additional hardware to support an optically ground, perfect mirror. Picture a mirror the size of the James Webb Space Telescope, crafted in one flawless piece. The same expert hands that shape mirrors for giants like the Large Millimeter Telescope and the Gemini North and South, capable of crafting 8.4-meter mirrors, are ready to build this one. This isn't just feasible, it's within reach. We could have the Mirror Lab construct this monumental mirror, mount it on a space telescope, and tuck it neatly inside Starship. With Starship's capability to launch 100 tons into orbit, envision a robust, heavy-duty space telescope, transforming our view of the cosmos. So what's the holdup? It's time to challenge the boundaries of what we can launch into space. Elon, it's time to deliver. Let's see this happen. How far along are we in turning this vision into reality? Switching gears to cosmic mysteries. What sparked the Big Bang? What role did dark energy play at the outset of everything? These are the enigmas we grapple with. The origins of the Big Bang remain elusive, the initial energy source unknown. We exist, so something monumental certainly happened, but our mathematical understanding can only trace so far back. Delve into the mysteries at the dawn of time, where the weak nuclear force, the strong nuclear force, and the electromagnetic force were once unified. What happened before this unity? How did gravity integrate with these forces? These are questions that, as of now, remain unanswered. And that's perfectly fine. Embracing the unknown is a part of the scientific journey. Now, shifting our gaze to the cosmos, are black hole stars, or quasi-stars, not just captivating theories, but plausible realities in astronomy? Science is a realm of conjecture and evidence. For instance, consider the fate of massive stars. When such a star exhausts its nuclear fuel, it no longer has the outward force of fusion to counterbalance gravity. What follows? The star's outer layers collapse, catalyzing a supernova and potentially birthing a black hole or a neutron star. We've observed neutron stars across the cosmos. They pulse as pulsars. They dazzle as magnetars. This evidence supports the theory that neutron stars do indeed form from the remnants of supernovae. Yet the full story of these cosmic phenomena continues to unfold as we piece together the clues scattered across the universe. Neutron stars serve as cosmic benchmarks. They don't exceed a certain mass. Beyond this limit, more massive stars face two fates. Either they explode, scattering themselves across space, or they collapse under their own gravity into black holes. But the existence of these black holes wasn't just assumed. Astronomers set out to prove it. The pursuit led to the discovery of Cygnus X1, the first identified black hole. Locked in a celestial dance with a companion star, Cygnus X1 was caught in the act of siphoning material from its partner, hurling radiation across the cosmos. This radiation, detected by astronomers in specific X-ray wavelengths, was precisely what theories predicted would occur if a black hole were devouring a star. Yet the quest didn't stop there. Theories speculated that supermassive black holes lurked at the centers of galaxies, including our own Milky Way. With the help of infrared telescopes, astronomers could observe stars orbiting an invisible point at the galaxy's heart, much like comets whirling around the sun. Measurements revealed this unseen force possessed a mass 4.1 million times that of the sun, bolstering the evidence for the existence of black holes. Imagine peering into the cosmic abyss and actually capturing the event horizon of a black hole. This isn't science fiction, it's reality, thanks to the groundbreaking work of the Event Horizon Telescope. This remarkable instrument has not only imaged the heart of M87, but also the supermassive black hole at the center of our Milky Way galaxy with astounding clarity. For the first time, we can see the actual shape of a black hole's event horizon, a sight that aligns eerily with the predictions of theoretical physics. Think of the stunning visuals from Interstellar, and you're on the right track. Each new piece of evidence brings us closer to the undeniable truth of these cosmic phenomena. Skeptics may still exist, but the overwhelming array of data, from the behavior of X-ray emitting stars to the orbital paths of stars swirling around the galactic center, to the actual photographs of black holes, makes a compelling case that black holes are not just real, but are also exactly as bizarre and fascinating as we've imagined. And what's next on the horizon? Enter the European Extremely Large Telescope, ELT, poised to be the largest telescope ever constructed. Operated by the European Southern Observatory and set to come online later this decade in Chile, the ELT will push the boundaries of infrared astronomy even further. With its massive 39-meter mirror, the ELT is set to unlock more celestial secrets, offering a deeper, more detailed view of the universe than ever before. As we stand on the brink of these incredible technological advances, one thing is clear: we are not just observing the universe, we are unraveling the very fabric of reality itself. Picture this. Nestled in the stunning landscapes of Chile, a constellation of advanced telescopes known as the Very Large Telescope serves as the precursor to something even more monumental. These 8-meter behemoths are not just optical wonders. They also delve into the near-infrared spectrum, capturing cosmic phenomena invisible to the naked eye. Building on this incredible technology, the upcoming Extremely Large Telescope, ELT, promises to expand our cosmic horizons even further. While it's designed to peer deep into the visible and near-infrared realms of the universe, the exact division of its observational duties remains undecided. However, its role in near-infrared astronomy is clear and crucial, especially in the hunt for exoplanets circling young stars. Many of the groundbreaking direct observations of these distant worlds have been achieved through infrared imaging, offering us some of the most thrilling visuals of the cosmos. Imagine the ELT capturing detailed portraits of planets orbiting distant stars, a feat that not only expands our understanding of the universe, but also brings us closer to answering age-old questions about our place among the stars. Shifting to a more terrestrial concern, let's consider the hypothetical scenario of a starquakes from a neutron star impacting Earth. While the very notion sounds like a plot from a sci-fi thriller, such a cosmic event would indeed have catastrophic consequences for our planet. If a starquake's energy were somehow directed at Earth, it could potentially trigger a mass extinction, unleashing a series of devastating environmental effects. The aftermath of such a disaster would reshape our world and challenge our resilience in ways we can hardly imagine. Think of a neutron star, not as a static orb of neutrons, but as a dynamic celestial body with its own complex layers. At its core, you might find a dense nucleus of neutrons, surrounded by a fluid-like shell also made of neutrons, and perhaps an outer layer akin to an atmosphere, composed of more conventional particles, all incredibly compressed. As neutron stars age, they cool down, gradually contracting in the process. This shrinking can lead to internal movements reminiscent of Earth's plate tectonics. As the star contracts, its internal structure crunches and adjusts, releasing staggering amounts of energy. This isn't just a minor release, it's a powerful burst of radio waves produced as the energy interacts with the neutron star's magnetic field, signaling a starquake. One of our best tools for observing these awe-inspiring starquakes is the NICER instrument aboard the International Space Station. NICER has given us invaluable insights into these phenomena, capturing the drama of starquakes unfolding on neutron stars. While the idea of a starquake affecting Earth might sound like science fiction, in reality, we're safe from these cosmic temblors. Unless Earth was in orbit around a neutron star, a thankfully improbable scenario, the effects of a starquake remain a distant yet fascinating spectacle. Imagine if Earth orbited a neutron star. Sounds like a plot straight out of a sci-fi thriller, right? Well, fortunately for us, neutron stars are hundreds of light years away, so there's no immediate threat. However, if we were that close, we'd be exposed to blasts of high-energy radiation potent enough to strip away our ozone layer, potentially leading to catastrophic levels of surface radiation and triggering a mass extinction event. But rest assured, the vast distances of space keep such dramatic scenarios well within the realm of imagination. Shifting our gaze within our solar system, let's talk about Io, Jupiter's volcanically vibrant moon. Unlike Earth, with its shifting tectonic plates, Io dances to a different geological rhythm. It's a world of volcanic hotspots, similar to the Hawaiian Islands on Earth, where magma breaks through gaps in the crust. This relentless volcanic activity paints a dynamic picture, akin to what some scientists speculate happens on Venus. Rather than tectonic plates, Venus might experience volcanic hotspots that periodically reshape its surface. And who knows? Io could be flipping inside out just like Venus possibly does, though there's no concrete evidence yet to support tectonic plates on Io. On another exciting note, the coverage of this year's NASA Innovative Advanced Concepts was truly captivating, filled with groundbreaking interviews. Looking ahead, the 2024 NIAC grants are eagerly anticipated. Who knows what innovative projects are on the horizon, vying for a chance to explore and expand our understanding of the cosmos? Every year, the anticipation builds for the NASA Innovative Advanced Concepts grants, typically announced in February. But the real excitement kicks off even earlier with a pivotal conference in November, complete with a teleconference that I always make sure to attend. This isn't just a passive listening session for me. It's an active foray into the minds of some of the most innovative thinkers on the planet. I dive into these conferences with a mission to connect with the presenters, understand their groundbreaking work, and bring their ideas to the forefront through in-depth interviews. Each proposal we discuss isn't just innovative, it's revolutionary. These are the conversations that spark imaginations and drive the future of NASA, pushing the boundaries from the routine of space stations to the thrilling possibilities of fusion drives. Despite the constraints and practicalities of space research, I'm always astounded that these discussions don't capture more attention. That's why this year, we took it a step further. We've not only continued our tradition of insightful interviews, but also reached out to the very helm of NIAC. Each conversation brings us closer to the cutting-edge technologies that could one day redefine our reach into the cosmos. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.